Properties that depend upon the number and not the kind of solute particles are called colligative properties. There are three colligative properties. The first one we will look at is the lowering of vapor pressure for a solution compared to that of the pure solvent. When you have a solution, there are fewer solvent molecules at the surface because at the surface there are also some solute molecules. This is a picture looking down at a container of solution. The X's represent the solute particles. The circles represent the solvent particles. The vapor pressure of a solution is lowered because there are less solvent particles at the surface. So there are less solvent particles evaporating, which thus lowers the vapor pressure. Raoult's law deals with the lowering of vapor pressure, saying it's directly proportional to the number of moles of non-volatile solute dissolved. Non-volatile means the solute particles will not evaporate. If both components of a solution are volatile, that means if both components can evaporate, the vapor pressure of the solution is the sum of the individual partial pressures. So the total pressure is equal to the partial pressure of component A plus the partial pressure of component B. We're going to look at a benzene toluene solution, which is an example of this type of solution where both components are volatile. This graph here shows the pressure versus the mole fraction of benzene. So starting over here, the mole fraction of benzene is 0, which means the solution consists only of toluene, while over here, the mole fraction of benzene is 1, which means the solution consists only of benzene at this point over here. Now the solid line is the total pressure for the solution, which is the sum of benzene and toluene. So if I add up these dashed lines here and here, I will get the total pressure for the solution. This is an ideal solution. The heat of solution is 0, which means the sum of the crystal lattice energy and the hydration energy is 0 for this solution. These two slides explain a little bit more about that graph. So vapor pressure for a solution is lowered. Boiling point elevation is a second colligative property. Since the vapor pressure of a solution is lowered, the resulting solution must be heated to a higher temperature in order for it to boil, because a solution will boil when the vapor pressure, which is the pressure pushing upward, is equal to the atmospheric pressure, which is the pressure pushing downward. So the boiling point of a solution is elevated above that of the pure solvent. Our equation for boiling point elevation is delta TB equals KB times M. This delta TB is the change in the boiling point. KB is a constant, depends on the solvent. M is concentration in molality. Here are some values for KB. And again, the value for KB depends upon the solvent. And I will give you the value for KB when we're solving these problems. So let's look at a problem involving boiling point. Anytime I'm calculating the boiling point of a solution, the first thing I need to find is the molality. So molality is moles of solute divided by kilograms of solvent. My solute is sucrose, solvent is water. So I found the molality 0.585. My equation for the change in boiling point is delta TB equals KB times M. KB for water is 0.52 degrees Celsius per molal. That's a constant for water. The molality, 0.585. So delta T is 0.3 degrees Celsius. So the boiling point will increase by 0.3 degrees, which means the actual boiling point is the boiling point of water, which is 100, added to the change. So this solution will boil at 100.3 degrees Celsius. Boiling point of a solution is always elevated. The melting point of a substance is the temperature at which the rate of melting is equal to the rate of freezing. Now, the solvent molecules are somewhat more separated from each other than they are in the pure solvent. This causes the rate of freezing to slow down. If the water molecules, the solvent molecules, are not touching, they cannot freeze. So the solute gets in the way of the water molecules touching each other and freezing. So the freezing point of a solution will always be lowered. Our equation for freezing point depression, delta Tf, very similar to the boiling point elevation, is Kf times m. And again, K is that constant, and it depends on the solvent. So I will give you the Kf values when we're solving these freezing point problems. So what is the freezing point of a solution? We have 23 grams of C2H5OH and 600 grams of water. First thing, find the concentration. My solute, C2H5OH, my solvent is water. So I found the concentration. Equation for freezing point, we're going to take Kf, my solvent is water, so 1.86 is the Kf value for water, times the concentration. So the change in freezing point is 1.55 degrees Celsius. The actual freezing point gets lowered. Normal for water is 0. Subtract 1.55, so my actual freezing point for the solution is negative 1.55 degrees Celsius. We can use the colligative properties of freezing point depression and boiling point elevation to determine the molar mass of the solutes. But the solutes must be non-volatile. That means the solutes cannot evaporate from the solution. Let's look at this problem. We want to calculate the molar mass of the compound. Now my solvent is benzene, it's not water. We're given the freezing point for benzene, and we're given Kf for benzene. I can find delta T by taking the freezing point, which is 5.48, and subtracting what the solution freezes at, which is 4.92. So delta T is 0.56 degrees Celsius. And I know delta Tf equals Kf times m. Delta T is 0.56. Kf, I'm told, is right here 5.12. So from this I can find my concentration. And my concentration is 0.11 molal. Let me move to the next slide. I want to get the molar mass of the compound. So I know the concentration, 0.11. We're going to set that equal to the mass of solute, which is 1.2, I'm told. If I put the molar mass down here, that's what I'm looking for, and I put the kilograms of solvent, which I'm told is 0.05, I can solve for molar mass from this equation. So molar mass Do some rearranging here. Molar mass equals 1.2. 0.11 down here. 0.05. And the molar mass of the compound is 220 grams per mole.